Okay, we are looking at radicals and rational exponents, getting away from factoring a little bit here, and looking at things like x to the 1/2 power. So how we can simplify expressions with radicals or rational exponents, understanding what the relationship between a radical and this expression would be. We'll use various strategies to simplify radicals, rewrite exponential expressions and radical expressions, and then apply our rules of exponents. Um, so remember, rules of exponents we learned in Unit 3. We'll still be applying all of those, so you might want to refer back to some of those notes um, as far as like when you multiply, you add, divide, subtract, and all of that. Okay, so notation-wise and word-wise, you'll have a radical, and this is your radical symbol. Um, you will have what we call an index. Um, so this will be the nth root of a number. You'll have a number underneath. This is called the radicand. And again, this symbol itself is called the radical. So this would be the nth root of x. Okay, so for example, this is the cubed root of 15. Things that you need to watch out for. The square root of 9 is just 3, not plus or minus 3. Whereas the square root of x squared, so if x squared is equal to 9, that is when x is equal to plus or minus 3. And that has to do with the fact that 3 squared is 9 and negative 3 squared is 9. So when we're solving is when we have those two possibilities. When we're just simplifying a regular radical, it's just your principal root is what they call that. Another thing you want to look for is your signs. So for example, if n is an odd index, so 3, 5, 7, and you're taking the index of that number, then the n's will cancel because they're inverse operations. So the fifth root of a to the fifth, for example, these n's cancel each other out, and the answer is just a. Right? If this was the seventh root of negative 3 to the seventh, again, those would cancel, and this would just be negative 3. So if it's positive, it stays positive. If it's negative, it stays negative. If n is an even number, though, so the square root, the fourth root, the sixth root, it's always positive. So let's do the fourth root of negative 3 to the fourth is equal to the absolute value of negative 3 which is 3. Right? And that's because taking something to an even powered would make it positive anyway. And then taking that fourth root keeps it positive. Excuse me. All right, so again, using your exponent rules, we have our product rule and a quotient rule. Both of these essentially are just stating that you can pull something apart. So if you have the nth root of a times b, that is the same as the nth root of a times the nth root of b. This works both ways. So an example of this would be, let's say we have just the square root of 12. Well, this is the same as the square root of 4 times the square root of 3. You can pull that apart, and this works both ways into two separate numbers. Quotient rule, same thing. If you have the nth root of a over b, one more time, you can rewrite that into the nth root of a over the nth root of b. Depending on the numbers, that can be helpful. Again, this works both ways. We can put them together or pull them apart. Notice that the indexes are the same in order to be able to do that. And so, yeah, again, you could do that with the same number. If you have the square root of 2 over 16, we could rewrite that as the square root of 2 over the square root of 16. Helpful to us because 16 is a perfect square. All roots must be real numbers for these rules to hold. So not a problem again because we haven't worked within the complex number system yet. Okay, so just using that idea, we can then simplify expressions. So with the quotient rule, we can pull things apart if this doesn't simplify first. Now 144 and 9 both reduce actually by 9. So there's a couple ways to do this problem. I also see that 144 is a perfect square, and we're taking square roots. So I could split it up like this. Take the square root of 144 is 12. Square root of a to the fourth is 2. Square root of 9 is 3. And y to the sixth is y to the third. All right. I could also do 144 divided by 9 and get 16a to the fourth over y to the sixth. We can see up here this is going to reduce to 4a squared over y cubed. Well, the square root of 16 is 4. Square root of a to the fourth is a squared. Square root of y to the sixth is y to the third. So we get the same answer doing it two different ways. Okay. Again, review exponent rules. They're on page 472. They should also be in your notes. Okay. Being able to switch these back and forth and looking at what's called a rational exponent, so an exponent in fraction form, and its relationship with radicals is important. So if you have a to the 1 over m, we're always going to use power over index for these. Remember, the index is the small number on the outside, so that m would come here. Your a is still your root value here, and this would be to the first power. Okay, so looking at another one, if we have a to the n over m, then we would have the mth root of a to the n. The second one can also be written as the mth root of, oops, I wrote the wrong colors, a to the nth power. You're going to use whichever is most convenient for solving your particular problem. Sorry, I'm pretty sure that's spelled wrong. And what I mean by that is you can either take the root first and then raise it to a power, or raise it to a power and then take its root. So sometimes it just depends on which way is easier. Okay, so why this is helpful to us. When we have something like this, the square root of x to the 16th, the index here is automatically a 2. So this is the same as x to the 16 divided by 2, which is x to the 8th. Same thing here, our index is a 3. So we're just dividing 15 by 3, and we have y to the 5th. Always watch your signs. So the square root of negative 36, that negative is unaffected by the radical, so we have negative 6. But here we have the square root of a negative inside, which we can't have. We can't have this negative underneath an even index. So the only reason this doesn't work is because it's an even index. And so the answer, right now you can put no real solution. However, if you want to get in the habit of saying, okay, well, the square root of 36 is 6, so that makes this 6i. We'll be covering this unit, but in a later chapter. So you might just practice getting, anytime you have an even negative, tacking that I on there like you would. Cube roots, though, our odd indexes are a little bit different. They keep whatever sign they have. So the cubed root of 27 is 3. The cubed root of negative 27 would then be negative 3. All right. If a radical expression is not a perfect square or a perfect cube, then you are going to break it down. So square root of 32, you want to look for your biggest perfect square. So let's think of our perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, and so on and so forth. 100. The biggest perfect square that goes into a number. So for 32, 16 goes in. So this would be 16 times 2. Remember our product rule. We can split this into the product of these two radicals. Square root of 16 is 4, and then we have 2 left over. This one you're doing a fourth root of 48. You don't have to list out your perfect fourths, although that's one strategy to do this. But instead we could start factoring. So I can look at this and clearly see that 4 goes in 12 times. 12 has 4 and 3. Each of these 4s is 2 2s. All right. So we look at the prime factorization of this number, and this would have worked for the 32 as well. And we can rewrite this now 2 to the 4th times 3. And even if I had an extra 2, I would just write it 2 to the 4th. Because now I can take the 4th root of that and the 4th root of that. Well, the 2 to the 4th is absolute value of 2, which is just 2. This one, make sure the index stays the same. It will never change. 4th root 3 comes down. All right, so it's just working with those properties and simplifying as much as you can to solve that problem out. Square root of 50 over 2, for example, can be written like this. And so we get 5. Go ahead and try 11 on your own. If you have variables with exponents in there, you're going to remember what your index is. So this is a square root. My index is a 2. Square root of 32, I've already solved up here. I know it's 4 root 2. But let's do it another way. Let's say we go 2 and 16 and don't realize that that's a perfect square, so we go all the way down. Then you're going to look again at your prime factorization. So I have a 2 here. I want to rewrite this as 2 squared. I have another 2 squared, and then I have a leftover 2. I have an x, a y to the 6th, and a z to the 5th. All right, so remember we're taking the square root of all of these. And we have power over index. Okay, so another way to write this would be 2 to the 2 over 2 times 2 to the 2 over 2 times 2 to the 1 over 2, x to the 1 over 2, y to the 6 over 2, and z to the 5 over 2. Right? This is a long way to solve this problem. This is not how I would typically do it, but I just wanted to illustrate a point here as to why we're able to pull this out. Right? 2 over 2 is just 1, so that 2 can come out of our radical, as can this one. 1 over 2, though, doesn't make a whole, which means we have a remainder of 1. So as far as underneath my radical goes, I know I have at least a 2 left. All right? Here I also have that x left because I just have 1 out of 2. I need a full 2 to take anything out. 6 over 2 divides to 3. 5 over 2 for my z divides to 2, but then I have a remainder of 1. So remainders go inside, whole numbers go outside. I'm just going to simplify this real quick. And we're done with that one. All right, so whatever that index is, that's what you're looking for in terms of groups. So this one is a cubed root. And so when I'm looking at the factors of 32, for example, I'm looking for how many groups of 3 can you make. All right, so 32 breaks down, I'll see one more time, into 16 and 2. Each of those is 4, and each of those is 2. But as far as groups of 3 go, I only have one group of 3 right there. My c's, I have c to the 3rd times c. W to the 6th is already in groups of 3, that divides evenly. And z to the 2nd is not going to divide evenly at all. I don't have enough of those. But there's a group of 3 and there's a group of 3 that I can pull out. So 1, 2 comes out. All right, 1c comes out because those are the cubed roots of those 2. All right, my index stays the same. I have a 2 times 2 left over, so that's 4. I have a c left over. Oops, I didn't take out my w. So let's slide that over. W3 should have come over. And then I have a z squared that didn't come out. either. So I know it's a little bit more of a challenging problem, but I want you to try this one on your own, as my video is getting a little long and I think you can get the gist of it. Okay, so moving into negative exponents, we talked a little bit about those last time. Same thing here. If we have 16 to the negative 3 over 2, in order to make that a positive exponent, we will take the reciprocal. And then we will remember again that it's power over index, and we can rewrite this in radical form to help us evaluate it. So we have 1 over the square root of 16 cubed. And remember before I said write this in which way it is convenient. Because 16 is a perfect square, it's more convenient to take the square root and then cube it than it would be to cube a number as big as 16 and then find the square root. So your final answer for this is 1 over 64. That negative in the front, especially when it's not in parentheses, is unaffected by the exponent. So when we flip this over, remember the sign of the exponent doesn't affect the sign of the number. And so our only difference now is that we're taking the square root, the negative, the opposite of the square root of 16 to the third. All right, so this is just on the 16, not on the whole negative. And so we get negative 1 over 64. Where in this very last one, you are taking the square root of a negative 16 to the third. And because of the negative, underneath an even root, it's just going to be no solution. Okay. All right, switching to exponential form, remember again, power over index. And so all of these powers are just a 1. So you can rewrite this as a, b, c to the 1/5. Or depending on what it's asking for, we have a to the 1/5, b to the 1/5, and c to the 1/5. Right. Again, negative exponents need flipped over. And that makes that a positive exponent. We can then write this as the 4th root of wx to the third on the bottom. We will do a rationalization of this problem later on in this unit. All right, and then just remember your rule of exponents still apply. Go ahead and try to simplify these as best you can, knowing that. Remember, power to power, you multiply. When you multiply like bases, you add your exponents. So this would be 1/2 plus 1/4. So you need a common denominator. This one we're going to get a common denominator before we multiply. These we're going to distribute after we maybe flip this over. So we're going to go through these tomorrow in class because that's a lot of notes for one setting. Have a good night.